everyone, this is lecture video 13, and in this lecture we will cover the topic implicit differentiation. Most of the functions we have dealt with so far have been described by equations of the form y equals f of x. This equation defines the function y in terms of the independent variable x, and we have learned certain differentiation rules to find the derivative of functions defined explicitly like this. So such kind of functions defines curve in xy plane. So this is an explicit equation. Through this explicit equation, y is defined in terms of x, and it gives us a curve like this in xy coordinate system. And another situation occurs when we encounter equations like this. You see in this equation, in fact, this equation gives us a relation between x and y, not explicitly like this, but implicitly. You know, you cannot solve for y from this equation. That's why you cannot find, for example, an equation of y just depending on x here. That's why we call such relations as implicit equations, and implicit equations defines curves like that, okay? For example, if you have an explicit equation, you can easily compute the first derivative of your function by using the differentiation rules. For an implicit equation, even if you don't have this explicit formula for y depending only on x, you can still search for the first derivative of function. You can still compute it, okay? For implicit equations, you can still find the derivative of x with respect to derivative of y with respect to x. This is still possible. How to compute it? By using implicit differentiation. Okay, so as I say, this is a curve defined by an implicit equation. Defined by an implicit equation, and by using implicit differentiation, even if you don't know the explicit formula for y in terms of x, this can still be computable. Sometimes for implicit equations to complete the first derivative, you try to solve, for example, let's look at this one. Find the slope of the circle at this given point. Okay, we are interested in the slope of this circle at this given point. And this equation, from this equation, y can be solved in terms of x like this. To find the first derivative of function y with respect to x, you can either solve for y with respect to x, or without solving it in terms of x, you can still compute its first derivative by implicit differentiation. So we will look at both ways. So what is the slope? Slope is, in fact, the first derivative of the given function at the given point. So to compute the slope, okay, recall. Slope, let's denote it by m, is in fact dy over dx at the given point. For example, the given point is 3, and this thing gives us the slope of the tangent line at x equals 3, okay? So let's look at the details of the computation here. Y can be solved as plus minus square of this thing, but look at the point. Our point is here, right here. You know, it is given there in the example. That's why now we can make a choice between plus and minus. You know, this lower arc has this equation where we put the minus, and over this part, you can see that all the y values on the red curve are positive. That's why you take the equation with the positive. And for this blue one, as you looked carefully, you will see that all the y values are positive, negative. So you take this squared with the negative sign. That's why we are interested in this curve now. And it can be really written as a power function like this. Now let's take the derivative, because our aim is to find the slope. Slope is the first derivative of the function at that certain point. So first derivative, we learned how to compute chain rule. That's why, first of all, we will deal with the most outer function. Here, the most outer function is taking this power, 1/2 power. It goes down here. And then you subtract 1 from the power. Then according to chain rule, what you do, you multiply, you keep multiplying with the derivative of the insider function, which is minus 2x. And if you rewrite the things here, the simplest form is like that. Now we want to compute this first derivative at this certain point. Just insert x equals 3, and this will give you the slope of the tangent line. Tangent line to curve, to our curve, y equals minus this. We are dealing with this curve, remember. At which point we are drawing the tangent line? We are drawing it at the point 3. You see, this pink line is the tangent line that we are dealing with, and the slope of it is computed as 3/4 by computing the first derivative of the function. Okay, now look at the second way. We will keep the implicit differentiation now without solving y in terms of x, which was the strategy that we used in the previous solution. We solved y in terms of x, and by using differentiation rules, we compute the first derivative. But here, we want to keep this implicit equation, and we still can find the first derivative of it, first derivative of y function with respect to x. Here, you should remember that x is the independent variable, where y is the function depending on x. Y is a function of x. You should keep this in mind. And then how do we apply implicit differentiation? You start taking the x derivative of both sides at the first step. You do this. Try to derivate with respect to x both sides. Okay, term by term, derivation of x squared with respect to x is 2x. Now, for this term here, how we should derivate? Okay, let's put a remark here about that thing. Y is a function of x. Be careful. And here, what we have its square. And now we want to take the derivative of this expression with respect to x, okay? We have square and we want to derive it now with respect to x. According to chain rule, you start with the most outer function as usual. So what should I write first? Power comes down, I subtract 1 from the power, then I should keep multiplying with the derivative of this insider function. So I should put this one here. You see, after taking power down, you apply the chain rule to find its first derivative. That's why this term is derived as 2y prime. And what is the derivative of the constant 25 on the right side with respect to x? It's obviously 0. See, derivative of constant numbers are 0. And from this equation now, you can easily solve for y prime. What is it? Minus 2x over 2y. And we want to find the value of it. At which point? At x equals 3. If x equals 3, what is the y component of it? You can easily find, you have this equation. If you insert x equals 3, you will find y equals what? Y equals minus 4. You are taking the minus. In fact, the point is given there. And then inserting these two values to our expression for the first derivative, we obtain minus 3 over, after simplifying these two. So it is minus 3 over 4, minus 4, so 3 over 4. You see, we obtain the same slope as we obtain above. 3 over 4, 3 over 4. So for this example, it is possible to solve this implicit equation for y and to find the explicit formula for y in terms of x. We were lucky, but this may not be the case all the time. For example, let's look at this one. We want to find dy over dx for the following curves. Okay, let's start with the first one. Okay, obviously this is an implicit equation. Implicit equation defining the function y in terms of x. Is it possible to solve this equation for y? Can you just obtain y alone and solve its equation, its function equation depending only on x? This is not possible. That's why we will take this implicit equation and try to differentiate both sides by using implicit differentiation. Okay. Let's try it. So d over dx. We are taking the derivative with respect to x. And for the first term here, we have to be careful because we have a product function here. And don't forget, y is a function of x. That's why in the first term is a product of two functions, both depending on x. So we will apply product rule for that one. Maybe I can handle it separately here. 2x times y. And why I am calling this as a product function? Because y itself is a function depending on x. That's why this is a product consisting of two different functions depends on x. We are applying product rule. To differentiate this, what we should do? First, you know product rule, how it works. Derivative of the first function, which is just 2 times the second, plus first function stays the same times the derivative of the second function. You know, if we call this f, we call this g. This is f prime, this is g, this is f times g prime. Okay, so the first expression is derivative like this, times y prime plus, we handled this above, it is 2y times y prime by chain rule. Okay, by the way, this is the derivative of this whole thing, d over dx. Then, on the right-hand side of the equation, what do we have? We have 1, which is the derivative of x plus y prime, derivative of the function y. Now, our aim is to solve this equation in terms of y prime because we search for the first derivative of the function, remember? So we will solve for it now. Just take all the terms depending on y prime on the left. So 2x, 2y minus y, and the rest will be moved to the right side, so 1 minus 2y. And from here, you can easily solve for y prime as this ratio. Okay, and this is how we apply implicit differentiation. dy over dx is this expression now. And here in the second part, okay, let's say this is the first part of part A question. And by taking the same equation here, now I want to find dx over dy. Remember, in the first part, we try to find dy over dx. This was the question. Now, we look the example the other way around. This time we will think x is a function of y, and we will try to take the derivative of y of both sides with respect to y. Okay, implicit differentiation. Be careful. This time, we are considering y. Okay, we are considering x as a function of y, and we are derivating each part of each side with respect to y, not x but y. Okay, we kind of change the roles of x and y here. This is still a product, you know, where the first function f is 2x, second function is just y. Apply product rule, derivative of the first function is 2 times dx over dy, right? Times the second function plus 2x stays times the derivative of the second function with respect to y. That's why it is just 1 now. Remember, you change the roles of x and y. Y is an independent variable now, and you are taking the derivative with respect to y. And then the second part, derivative of y squared with respect to y is just 2y, and move to the right side, it is dx over dy plus 1. And our aim is to solve this equation with respect to this derivative, which can be handled easily. Okay, dx over dy parentheses, take everything depending on dx over dy to the left. Okay, let me write it quickly. Okay, what we have, 2y and 1 minus 1 here, and on the right we will have 1 minus 2x minus 2y. And from this equality, you can solve for dx over dy over 2y minus 1. And now we will compare dx over dy with the dy over dx. Okay, let me write this as dy over dx. You know, this is just different notations for y prime or dy over dx, the same thing. Now compare these two, please. What is the relation? You notice the relation, right? One of them is the reverse of the other one. Is that correct? So if you compare, we find that dy over dx is 1 over dx over dy. So this is a famous fact in calculus course, okay? And we verify this fact now by solving a particular example. And it is already written here. This is the relation between dy over dx and dx over dy. Okay, let's move on. So you can solve all those equations and find dy over dx. Okay, for all of them, you will try to find dy over dx by using implicit differentiation. I will skip part B, part C, part D. Please try them by yourself, and I will solve part E for you by using implicit differentiation. Okay, obviously you cannot solve for y from this equation. That's why we will treat this an implicit equation, and let's try to find dy over dx by using implicit differentiation. Differentiation, meaning that we start by taking the x derivative of both sides. Okay, left-hand side. Do you recall that the derivative of the exponential function, the power of the exponential function also consists of x? How do you take the derivative of this expression itself times the derivative of the power? So we will be applying that for the left side. So itself times the derivative of the power with respect to x, which is 2. Now, right-hand side, you start with the most outer function according to chain rule to derivate right-hand side. First, you should derivate sine. It is derivated as the cosine function. You don't touch the insider part. Then you keep multiplying with the derivative of this insider function. So 1 plus 3 dy over dx, right? That's what we have. Instead of dy over dx, you can use y prime notation. It is easier to write. And from here, we will try to solve dy y prime from this equation. So what we have, 1 plus 3y prime is e to the power 2x times 2 over cosine x plus 3y. And then solve for y prime, please. Let's use here. Y prime is 2 times e to the power 2x over cosine of x plus 3y minus 1, you know, so minus cosine x plus 3y divided by 3. So this is our y prime function computed by using the implicit differentiation. Okay, let's move on. We can look at this one. So this is an equation of the function r depending on theta, okay? So this implicit equation defines the function r in terms of theta, and what we want to find derivative of r with respect to theta. And let's find this first derivative by using implicit differentiation, meaning that we will take the derivative of both sides with respect to theta. Okay, what is the derivative of this power function with respect to theta? You take the power down, you subtract 1 from the power, plus here. These are all power functions, and we are applying kind of chain rule here. 1 over 2 goes down again, you subtract 1 from the power, minus 1 over 2, and then remember, our function depends on theta. That's why, according to chain rule, you keep multiplying with the derivative of this insider function. So I will multiply with the dr over d theta here. Then on the right-hand side, what is the derivative of this constant with respect to theta? It is obviously 0. From here, we will try to solve for dr over d theta, right? So what we have? We have dr over d theta, so the coefficient of it is square root of r, something like this. And you can move this part to the right, minus 1 over 2 square root of theta at the denominator, like that. Then simplify, these are gone. From here, dr over d theta is solved as, so you will just send this part to the right-hand side, okay? By the way, why did I put an, this is, let me see, it is just R, okay, so like this. I put accidentally 2 there. So send this thing to the right-hand side, and you will then find the result as square root of r divided by square root of theta. There is this extra minus here, okay? So that's it. I think there is one more thing to say here. So this, let me check. I sent this to the right-hand side like that. Yeah, okay, the result is like so. And then let's move on. You can solve this similar question by yourself. And let me solve this one for you. Okay, we again have an implicit equation here, defining y as a function of x. And you see this time, we want to find the second order derivative of y with respect to x at some given particular point. Okay, we will handle it step by step. First of all, by differentiating this equation with this, by using implicit differentiation, we will find dy over dx. After finding it, we can take one more derivative. Okay, let's start. Be careful, this is a product function, so I will be applying product rule. Derivative of the first function with respect to x is 1 times the second function. Now I am differentiating this part, plus x times dy over dx. Okay, this whole part is the derivative of this blue first expression, and then 2y times dy over dx, you know, by chain rule, is 0. Now we will insert the given point. So insert x equals 0, y equals minus 1. What you have, minus 1 plus 0 plus 2 times minus 1 y prime, or I was using the dy over dx notation, dy over dx is 0, so dy over dx is solved as -1/2. So first derivative of y function gets this value when x is 0 and y is -1. Okay, now we will keep differentiating this line again once more because we need the second derivative. This line contains the first derivative of function. That's why I need to differentiate one more. Derivative of y is dy over dx, okay? And then we come to here. This is a product function. We will apply product rule. Let's apply it. Derivative of the first function times the second function plus first function stays the same times the derivative of this second function. So you see, this is the second derivative of y now. Then if you keep moving like that, still you have a product here. Okay, let's clarify things. And so now I will be dealing with this product. Derivative of the first function with respect to x is 2 times dy over dx times the second function plus first function stays times the second derivative of the second function, which is this thing. Okay, this whole thing comes from this part. If you differentiate one more with respect to x, equals, obviously on the right hand side you have 0, still 0. Now what we will do, we will insert the given information now to this equation. What do we know? X is 0, y is -1, and the first derivative function dy over dx, if x is 0, y is -1, what is that? We just solve for it as -1/2. So this is -1/2. Let's insert all those values to our expression. So what do we have? -1/2 plus another -1/2 plus x is 0, and then plus 2 times -1/2 -1/2. You see, I'm inserting these two, plus 2 times -1 times d squared, the x squared is 0. You see, in this equation, the only unknown is this. And this is what we try to find. And from this equation, the second derivative of y with respect to x is solved as -1/2. Sorry, -1/4. Is that okay? So let's move on. And finally, in this lecture, okay, I leave this as an exercise for you. We can also solve this example in the problem solving session together. Now let's look at this part. Slopes, tangents, and normals to curves. You have a curve here, and at any particular point, you can draw the slope, as you can draw the tangent line to your curve, which is this blue one, and the line that is perpendicular to the tangent line is called as the normal line. Okay, the blue one is the tangent line drawn at this particular point. Okay, let's indicate the point with green. And the red one, which is perpendicular to the tangent line, is called as the normal line. So tangent line and normal line are always perpendicular to each other. And yeah, you can see the same situation here. At any point, this applies. The blue one is the tangent line and the red one is the normal line. Okay, so what do you remember about perpendicular lines? Do they have something special? Okay, L1 and L2 here are perpendicular, obviously. Let's say M1 is the slope of L1 and M2 is the slope of L2. If the lines are perpendicular, then is there a relation between M1 and M2? There is a famous relation between the slopes of the perpendicular lines like that. Their slopes, the product of their slopes is always -1. What if the lines are parallel? If the lines are parallel, then their slopes are the same. The relation between their slopes are like that. Okay, so look at this figure again to clarify things once more. This is our function y equals f of x. At any point, let's say at the point A, you can draw this slope tangent line, and you can talk about the slope of it. So as we know before, slope of the tangent line is given by the first derivative of your function, and you evaluate the first derivative at the given point here. Then what happens to the slope of this normal line? You know, its slope has to be this expression, so that if you multiply these two, you need to obtain -1 because they are perpendicular. Okay? So maybe I should express it. If you express this as m, then this is obviously -1 over m, so that if you multiply, so that the product becomes -1. Okay, here is a nice question for you about this fact. Let me emphasize the important parts. Yes. Okay, we want to find the equation of the tangent and normal line to the given curve. Find the equation of tangent and normal line to the given curve. Okay, this is an implicit equation defining our curve. Okay, and the slope of the tangent line, is given as the first derivative of the function at the given point. Look at the indicated point. X component of the point is pi over 4. So if you compute this, you will find the slope of the tangent line. Once you find this slope, as you have the point here, you can easily write the equation of it. Okay, now we are applying implicit differentiation. Okay, take the derivative of both sides with respect to x. And as you can see here, you should be really careful about the product functions. This is a product function again, so you will be applying product rule. Derivative of the first function, which is x, is 1 times the second function plus. First function stays the same. Now I will derive sine 2y. What is the derivative of sine? It is cosine. And then you keep multiplying with the derivative of the insider function, which is 2y prime. Okay? And this whole thing gives us the derivative of this product by applying product rule. Now, right-hand side. Also on the right-hand side, you have a product. We will again apply product rule. So derivative of the first function y prime times the second function without changing it, plus y is the first function, stays the same. Derivative of cosine is minus sine. You shouldn't touch the insider function, it stays as the same. And then you will multiply with the derivative of the insider function, which is 2. Okay, from this equation, we want to find the first derivative at this given point. So let's insert the given point. X is pi over 4. And we also know the y component of it. Y is pi over 4. If you insert these two values, what happens? Okay, 2y is pi over 2. Sine pi over 2 is 1, right? So it goes like 1 plus pi over 4 times cosine pi over 2 times 2y prime. Okay, y prime times cosine pi over 2 plus y is pi over 4, then minus sine pi over 2 times 2. Okay, what do we know about this? Cosine pi over 2 is in fact 0. All the cosine pi over 2s are zeros. So what do we have then? From this equation, I think, so let me see. This is 0, this is what we have on hand, but we can also compute this one. Sine pi over 2 is just 1, right? Wait, sorry, let's fix this. Y is not pi over 4, but pi over 2. Okay, this changes everything. Let me fix this computation. Okay, so if y is pi over 2, sorry about that, insert all the values and then you will obtain something like this time 1 plus pi over 4 minus 1. Okay, this is the cosine of pi, by the way, times 2y prime equals pi. Okay, this is what you should get after you insert everything. And then from this equation, if you solve for y prime, you will obtain some value like that. Okay, divided by, I guess, pi over 2 minus 1. Now, this is what? This is the slope of the tangent line. Now, I am ready to write the equation of the tangent line then. Okay, let's write it. Equation of tangent line. To write it, you need the slope, which is computed here, right? Minus pi over 2 plus, by the way, this should be plus 1, I guess. Minus pi over 2 plus 1. And the point is pi over 4, pi over 2. It is already given in the statement. Now, slope is here, point is here. You can easily create its equation. How you create it? Y minus y0, slope times x minus x0, where this is x0, this is y0, and the slope is here. So y minus pi over 2, okay? And then slope times minus pi, minus 1, minus pi over 2 plus 1, x minus x0. So this is equation of the tangent line. Now, similarly, we want to find the equation of the normal line. We obtain the first part, and now we search for the equation of normal line. You know, we are dealing with a curve here. At some point, we already find the slope. Okay, we find the slope of the tangent line, and now to write the equation of the normal line, I need to find the slope of it. So the slope of this normal line is, in fact, as we discussed above, is minus 1m, because their products has to be minus 1, right? That's why, okay, for the slope of normal line, what do we have? It is minus 1 over m, so where m is this thing, right? That's why it is minus pi over 2 plus 1 divided by pi plus 1. Okay, point is the same. And we have the point. We are drawing both tangent and the normal at the same point, which is this one in our case, pi over 4, pi over 2 point, right? Point is the same, pi over 4, pi over 2. That's why equation goes like similarly above, y minus y0, slope. This time slope is a bit different. Minus pi over 2 plus 1, pi plus 1, and then x minus x0, pi over 4. Okay, and this is the slope of normal line. So that's it. I stop here. Thank you for your attention. I will see you in the next lecture video.